So why are we in mod 5? When everything else is mod 10? 10 to 5? 2 to 5. Yeah. Anyways, so, well, this section in mod 5 we actually skipped. We kind of felt like it was strangely placed in mod 5, and it belongs more in mod 10. It actually leads in very well to 10.1, which we also skipped because we started at 10.2. And we used to do 5.2 and then we would do 10.1, but we actually dropped 10.1 completely. And so we're just doing 5.2. So that's kind of a little history of where it came from. But it's this idea of having an inverse, and kind of the reason for this is because the cube root graphs and the square root graphs that we've been graphing are inverses of cubics and of quadratics. So that's kind of where the inverse idea comes from. Now, finding the inverse of a cubic or a quadratic is a little bit of a pain in the tush, which is why we're skipping it. That's what 10.1 is. So we're going to stick with just the inverse of a first degree equation or a line. Okay? We're just going to stick with a basic idea of what an inverse is. So, a relation, here's just some definitions for you. A relation is any connection between a set of input and output values. Input values are represented by X. They also give you the domain. We've talked a lot about domain. Output values are represented by Y or F of X, and those give you the range, which we've talked a lot about as well. A function, you've heard that word before, is a relationship between a set of values where each input has exactly one output. All right, so now we have 3 different examples of relations. We have a one-to-one relation, a many-to-one relation, and a one-to-many relation. And I'm going to explain it mainly using these bubble things down here. Does anyone know what these are called? These are called mapping diagrams. It's a different way of listing ordered pairs. For example, this is the ordered pair 2, 5. And this one's -3, 2, right? Domain being your input or your X, range being your output or your Y. So here's how a one-to-one relation works. Do you see how each domain value has one arrow going to one range value? There's nobody that's sharing domain or sharing range. Everybody's got their own arrow connecting them. The way you would find the inverse, here's the relation, the way you would find the inverse is you simply flip your domain and range. So instead of 2 going to 5, it becomes 5 going to 2. And -3 going to 2 becomes 2 going to -3. What would my next one be? -6 goes to 5. So my ordered pairs are being flipped around, right? The X is becoming the Y is becoming the X. And the last one here would be 4 goes with 1. That is a one-to-one relation. Comes from one number, goes to one number. Is the function, is the relation a function? And then the other question is its inverse a function? Now, how do we tell if it's a function? Well, in order to be a function, domain values can only be used once. So, is 2 used more than once? No. It's only grouped with 5. That's once. -3 is only used once. 5 is only used once, and 1 is only used once. So is the relation a function? Yes. Is the inverse also a function? Yes, because every domain value is only used once. How many points are represented in my mapping diagram? If I looked at just the relation, how many points are represented there? 4 points. Okay? All right. Then we have a many-to-one relation. Okay. Is this a function? No. Look very carefully. How many times is 2 used? How many times is 1 used? How many times is 2.5 used? How many times is negative 2 used? Is it a function? Yes. Because a function means that only the domain values are used only once, and that's true in this case. Now let's find the inverse. So 2 went with 5, so now it's 5 going with 2. Yes? 1 went with 5, and now it's 5 going with 1. Oops, hang on. Come on, Franken. I don't need to write that number again. I just draw 2 arrows from it. 2.5 went with 3, so now it's 3 goes with 2.5. And negative 2 went with negative 2, so if I flip that, it's the same thing. Negative 2 goes with negative 2. Is the inverse a function as well? How many times is 5 used? Twice. As soon as I have a domain value that's used more than once, it's not a function. So that was a many-to-one. Now I have a one-to-many relation. Is the original relation a function? Is 1/2 used once? It's used twice, isn't it? So it's not a function. Let's see if the inverse is. Let's see, 1/2 went with 3, so 3 goes with 1/2. 1/2 went with 1, so 1 also goes with 1/2. And then 2 went with negative 3, so negative 3 goes with 2. Is the inverse a function? Yes, because 3 is used once, 1 is used once, negative 3 is used once. The inverse is a function. So there are times where both the relation and its inverse can be a function, or only the relation or only the inverse are functions. There's all different combinations there. All right. Each of the relations above is graphed. We need to add the inverse. So if I look at this first graph, I have the point 2, 5, negative 3, 2, 5, negative 6, and 1, 4. So I need to graph the inverse. So I'm going to graph 5, 2. 5, 2 is right there. 2, negative 3. By the way, ignore the dotted line for right now. Let's see, negative 6, 5, and 4, 1. Do you notice anything interesting there? If I were to take this line, this is kind of an important line, and I'll talk about what it is in a minute. But if I were to look at the original relation, if I were to think about how far that is from that line, isn't the inverse of that point about the same distance, just on the other side? What about this point, this one that was over here? If I think about how far that is from the line, isn't the inverse about the same distance on the other side? We did that before, didn't we? We graphed something where we found out how far it was from something, and then we went the same distance the other way. Do you remember what that was? That was when we reflected it over an axis. This time we're reflecting it, but we're not reflecting it over an axis. We're reflecting it over this line. Does anyone know what that line is? That is the line y equals x. Y equals x is kind of an important line. It is the mother function of all lines. Okay, so an inverse is simply a reflection across the line y equals x. So let's look at this guy. Again, I have, let's see, 2, 5, 1, 5, 2.53, and negative 2, negative 2. So now I'm going to graph the inverse. So 5, 2, and also 5, 1, 3, 2.5, and negative 2, negative 2. Why did negative 2, negative 2 end up the same? It didn't move. Every other point moved. Well, if I were to draw in this line, now keep in mind the line y equals x goes straight It's got a rise of up 1 over 1, up 1 over 1. So it's always going to be a perfect diagonal through your origin. And so if I draw in this line y equals x, do I still have that reflection going on? Sure looks like it. These two are about evenly spaced. Those two. Why did that one stay the same? Because it's on the line y equals x. If it's on the line y equals x, y and x are the same number if y equals x. So any point that's on the line y equals x is going to stay on the line y equals x. It's not going to move. Okay? All right, let's graph this last one. We had 1/2 3, 1/2 1, 2 negative 3. Let's graph 3, 1/2, 1 1/2, and negative 3, 2. Does it still follow that reflection? Yes, it does. Okay, so that's what a simple set of points looks like if you're going to graph it in its inverse. Okay? All right. Let's talk about two important things. Let me grab my highlighter. You should be familiar with this guy right here, the vertical line test. Have you used that before? How does the vertical line test work? You've heard of it before, but nobody knows how it works. Awesome. Okay, so a vertical line test means if I give you any sort of a graph, any sort of a shape, any sort of a graph or picture or whatever, you can tell if that is a function by using the vertical line test. So for example, if I gave you a graph of a parabola, just a regular schmegular parabola, I would be able to identify if that is a function by looking and seeing, is there any place where I could draw a vertical line through that parabola and I would touch the parabola more than once? Is there any place I could do that? No. Everywhere I would draw a perfectly vertical line would only touch that parabola once, correct? That means yes, it is a function. What if I have something like a cube root that looks kind of funky like that? Is that a function? Because there's a few places here where if I drew a vertical line, I am definitely going to hit that more than once, aren't I? So no, that one is not a function. What about this cube root? Where the bends aren't quite as bold. Is that one a function? It is, because even though it looks like it's going to cover it a little bit, it's only going to hit it once. So that one is a function. Okay? Now, what if I was looking at a graph and I thought, I don't want to know whether this is a function. I want to know whether its inverse is a function. But I don't want to have to graph the inverse. I just want to know if the inverse is a function. Because everybody asks themselves that, right? Of course. So how do you find that out? You use something called the horizontal line test. The horizontal line test works the exact same way. However, it doesn't tell you whether the original graph is a function. It tells you whether the inverse of that graph is a function. So if I look at this first one, is its inverse a function? In other words, does it pass the horizontal line test? No, because if I were to draw a horizontal line through here, it's definitely touching it more than once, right? So the inverse of that graph is not a function. Does that make sense? Good answer. What about this guy? Is the inverse a function? Okay. It passes the horizontal line test, therefore the inverse is a function. I could just write yes if I wanted to. What about this guy? Is the inverse a function? Yes, the inverse is a function. Does that kind of make sense? Now, if I didn't want to use the horizontal line test, here's my alternative. I could turn my paper 90 degrees, because as soon as I turn my paper 90 degrees, I have the graph of the inverse. So I could actually look there and I could use the vertical line test if I turn my paper 90 degrees. Why does that work? Because the vertical line test on my turned paper is what? A horizontal line when my paper is not turned. Does that kind of make sense? So you can either turn your paper or you can just use the horizontal line test. Okay, turn the page. Okay, so here's where we get into the actual kind of nitty-gritty of how do you find an inverse of something. Something you want to remember is y is often written as f of x. Okay. And the main thing that you need to remember are these steps right here. So for any equation that we're finding the inverse of, your first step is to take out f of x and make it a y in order to make the equation simpler. So if I'm going to find the inverse of this guy right here, first thing I'm going to do is I'm going to change this f of x to a y. So far so good? Terribly difficult, right? Steps 1 and 4 are a piece of cake like that. 2 and 3 are the ones where there's a little bit of work. Actually, 3 is really the only one. What kind of a graph would this make? Anybody? A line. It's a first degree polynomial, isn't it? That would make a line. Okay. Step 2 says to solve for x. In other words, get x by itself. So if I wanted to get x by itself, what do I need to do? I need to start off by subtracting 6. That gives me y minus 6 equals negative 3x. Right? What do I do now? Divide by negative 3, and here's how I'm going to divide this by negative 3. Divide each part by negative 3. How would I write y over negative 3? I would write that as negative 1/3 y. Minus 6 over negative 3, what does that turn into? Minus over a minus becomes a plus 2 equals x. You still with me? That's the only step that actually requires some work. Step 3 says change every y to an x and every x to a y. So this is going to stay with a negative 1/3, but it's not going to be y, it's going to be x plus 2 equals, and change that x to a y. Now just to be clear, this process up until here, you have not gotten an inverse. You've just done some moving around. When you finally have an inverse is when you switch those x's to y's and y's to x's. That's when it finally becomes an inverse. The last step is you need to, because we took f of x out, we have to put it back in. But we can't call it f of x anymore because that was the original equation. So we have to use this notation right here, which means the inverse of f of x. That doesn't mean raise it to the negative first power. That means what we're saying is this is the inverse. So I would say f inverse of x equals, and that's what I'm replacing y with. So what am I going to say it equals? This right here. Negative 1/3 x plus 2. Terribly difficult? Yes? No? Okay. Let's try it again. Here's an original function. This one's g of x, which means that when I write the inverse function, I'm going to put g inverse of x. What am I going to do first to find the inverse? Change g of x to y. What's my second step? Anybody? Get x by itself. So what am I going to do? Subtract 5. That gives me y minus 5 equals 1/2 x. How do I get rid of that 1/2? Multiply by the reciprocal, right, which is 2. Now, just like I divided both terms over here, I'm going to have to multiply both terms over here by the 2. So what does that give me? 2y minus 10 equals x, because 1/2 times 2 is 1. Okay, x is by itself. I'm done with step 2. Step 3, change your y's to x's and your x's to y's. So that gives me 2x minus 10 equals y. And then what's my last step? Write it with that inverse notation. So the inverse of g of x is equal to 2x minus 10. Any questions over that part? Pretty easy? Okay, good. Now let's look at what the graph of it looks like. If I were to graph both the original and the inverse, I should see what? What did I see on the other side? I saw a reflection, correct, over that line y equals x. So let's see if when I graph a line, if I still have that reflection. Now this graph right here is actually the original equation we started off with right there. And we're going to now graph the inverse. Now, Ms. Armstrong put the XY table on it if you want to graph a line from an XY table. I prefer, especially when it's in this form, not to graph it from an XY table, but to use our y equals mx plus b. Do you remember that? Nobody remembers that. Okay, one person does. Fantastic. All right, so this one is in y equals mx plus b, so what am I going to start with? The b value, correct, which is 2. And what does that give me? My y-intercept. So on my y-axis, I'm going to mark a point off at 2. What is my slope here? Negative 1/3. Now question, does the negative go with the 1 or the 3 or both? The 1. Don't ever say both. Why? Both will cancel out and make it positive. So technically you can put it with either the 1 or the 3, just not both, because that changes it to positive. I like to throw it on the top just because I'm always consistent with the same thing. So what does that mean? I'm going to go down 1 and then over 3. Make a point. Do it one more time. Down 1, over 3. Make a point. And let's draw in our line. Now, out of curiosity, if I were to do this using that XY chart, do the points flip like they did with the mapping diagrams? Does the point -1, 9 become the point 9, -1? Yes. It would be, because that would be my next point, wouldn't it? Does the point 0, 6 become 6, 0? So if I were to use the XY chart, if the XY chart is given to you, it's easy to use the inverse on the XY chart, just like you did with the mapping diagram. Now, my most important question is, if I were to draw in my dotted line right here, and I'm trying to draw it in as straight as possible, do I get that mirror image? Now, you have to think closely on this. If you took this and you flipped it over this line, it's going to mess with you a little bit, but watch. If I flip it over, it does go that way, doesn't it? So in other words, the point here, if I were to look at how far that is from the line, it's about the same distance on the other side for that other point. So I do have a reflection even when I have the whole line and not just a handful of points. Questions about that? Okay, you'll have to read the instructions on the homework because sometimes it will say graph the inverse only. Sometimes it might say graph both the original and the inverse. Okay. All right, one quick question here. Well, I guess it's 3 questions here. What is the inverse of the line y equals 3? Well, if I were to follow my steps, first step says take out f of x and make it y. Is there an f of x to take out? No, it's already y. What is step 2? get x by itself. There's no x to get by itself. Step 3 says what? Change your x's to y's and your y's to x's. That I can do. I can change the y to an x, and I can get that. And what's the last step? Change the new y. I don't have a y, do I? So step 3 was the only step I could do. So the inverse of the line y equals 3. Now think about this for a minute. The line y equals 3. Here's where y equals 3. The line y equals 3 cuts through my y-axis at 3. So it's a perfectly horizontal line. What is the line x equals 3? Cuts my x-axis at 3. It is a vertical line. So in other words, the inverse of a horizontal line is a vertical line. And I can say the opposite is true as well. The inverse of a vertical line is a horizontal line. Now here's a question. Is a horizontal line a function? Yes or no? How would I find out? Does it pass the vertical line test? Is there anywhere I could draw a vertical line and it's going to touch it more than once? So yes, a horizontal line is a function. Is a vertical line a function? Yes. Is there anywhere I could draw a vertical line that it would touch that more than once? Uh-huh. If I drew a vertical line right there, it doesn't just touch it once, it touches it everywhere, doesn't it? So it touches it not once, not twice, not 3 times, but an infinite amount of times it touches it because it's literally right on top of it. So is a vertical line a function? No. In fact, when it comes to lines, all lines are functions except a perfectly vertical line. It's the only kind that can't be a function. Okay? All right. So that's the end for today. Happy studying.